Everybody, welcome to week 6 of the organic chemistry seminar. Off to a great start. Sorry about it going up late. I've had a bit of a horror end / beginning of week / end of last week, but I am getting caught up on all the video recordings, so we should be good to go. This week is actually we're past the midpoint, but everything that we've learned up to this, up until the end of this week, underpins all of the solubility, reactivity, melting point, boiling point, so on and so forth. So I will sort of go back a little and make sure that we've cemented the concepts for organic chemistry. I also have 4 brand new whiteboard markers, which I'm very, very excited about. I'm going to just go straight into the whiteboard. I'll recap of what we've done. Organic chemistry from the year 12 session of this one. SF6. So, what we've learned so far is that there's 3 types of intermolecular force. Alrighty, hasn't it got any better over the whole? So 3 types of intermolecular force, and they're caused by different kinds of bonding. And if again we go back a little bit, we look at ionic bonding and covalent bonding. Ionic being the donation of electrons from, say, metal and a non-metal, so sodium and chlorine. Sodium is in group 1, has 1 electron, 1 valence electron. Chlorine is in group 7, has 7 valence electrons. You get the donation of electron from sodium to chlorine, Na plus, Cl minus. And you get a really strong bond and a lattice form. We don't worry too much about this in organic chemistry. It's only really relevant in organic chemistry and metallic chemistry. So physical chemistry. So we're looking at covalent bonding. Covalent bonding is the sharing of valence electrons. So in the outer shell, atoms will need 8, as in the case of hydrogen. It only needs 2, and boron only needs 6. But everything else requires 8 to get to an octet state. So we have covalent, about 4 different colors. Polar and non-polar. Polar meaning a negatively charged end and a positively charged end. Non-polar means even distribution of the electrons. And it's all to do with the concept of electronegativity. And I'm sure you're sick of me going on about electronegativity. Sure, my wife's sick of me going on about electronegativity as well. Even I'm sick of going on about electronegativity. But it underpins everything, really. I mean, not just in organic chemistry, but probably the most important. I mean, they're all pretty important, but for what we're talking about here, it's really important. So we have the periodic table. I mean, obviously it doesn't look like that. But there's francium in the bottom left, fluorine in group 7, nitrogen, oxygen, fluorine. These are the most electronegative atoms. Over here is the least. So electronegativity values increase this way. we have hydrogen up. And what this electronegativity value means with regards to this is the propensity for that atom to hog the electrons when it binds with an atom of less electronegativity. So we have hydrocarbons that we've learned about. So they are hydrogen and carbon. Carbon sits here in group 4. So when it binds with hydrogen, we get 1 carbon down to 4 hydrogen. And the electrons are shared evenly. The electronegativity difference between these two is not high enough so that one will share the electrons. All of them have a neutral charge. So that is a non-polar molecule. Non-polar molecule. And it only has, if we remember, dispersion forces as its intermolecular forces. So if we ramp that up a bit, and we get if there's 2 atoms where there is a significant electronegativity. So if we keep it simple, we take hydrogen and chlorine. The electronegativity difference between these two is sufficient that when they bond and they create HCl, if we put that as their outer shell, chlorine will hog the shared electron. So chlorine will become negatively charged and hydrogen will become positively charged. Now, this is what we call a temporary dipole. So this electron will eventually make its way back to hydrogen. And anything, so you would have another HCl molecule line up here that will be negatively charged. And because this is positively charged, you get some bonding here. So the electrons here, electrons over here, they're bound together. But eventually that electron moves back here. And this bond is broken. Now when you're talking about hydrogen bond, it's a very similar concept. Well, it's similar, but it's not the same. So, in order to have hydrogen bonds, we need Shokara hydrogen. We also need oxygen, nitrogen, and fluorine. When hydrogen bonds to one of these three, the electronegativity value difference is so great that if it was to be, say, HF, the fluorine would permanently steal the electron and it would have a permanent dipole, virtually permanent dipole. Nothing's permanent. But so you end up with positively charged and a negatively charged. I'm going to go more into detail on that. But that's the basis. You have hydrogen bound to oxygen, nitrogen, and fluorine, which creates an almost permanent dipole. And that's the difference between, one of the differences between a hydrogen bond and the dipole-dipole forces. So let's jump onto the should look at the slides now that I've done that all. So, hydrogen bonding is a special type of intermolecular force. So it has similar characteristics to dipole-dipole forces and of a covalent bond. And it's about 10% of the strength of a regular covalent bond. So, and again, I will reiterate that these are intermolecular bonds. They do not create new molecules. They simply connect molecules. So a covalent bond is intramolecular. It takes two atoms, or two or more atoms, and makes a compound. Hydrogen bonds simply connect compounds together. And I'll stick with water for this because it's sort of the easiest to conceptualize. So you have a hydrogen atom, which then becomes sandwiched between two very electronegative atoms. So fluorine, nitrogen, and oxygen. If you remember ONF, I don't know, I always found that easier to remember. ONF equals a hydrogen bond, or the top of group 5, 6, and 7. So, hydrogen has a high charge density, and it's so small, and this electronegativity value is so high in F, N, and O that when they come near each other, so two molecules of water, that the H, the positively charged hydrogen, water, will form a weak bond with the oxygen of another molecule. And this creates like a web or a diamond, or like almost like a net shape. So, again, molecules that have hydrogen bonding are almost exclusively organic molecules. I don't speak in absolutes, but they're virtually almost exclusively organic molecules. So we know it can occur when hydrogen is bound to a very electronegative atom, so nitrogen, oxygen, or fluorine, or when you have a very electronegative atom with a lone pair of electrons. Now, that's probably a little bit outside the scope of 1112 for Queensland. Other states and IB, you probably go into that. So, water is the classic example. Water should not exist in the form that it does. It should not have a boiling point that it does. It should not expand when it's frozen. If you put a pumped water bottle in the freezer, it expands and completely ruins the water bottle. It should not do that. But it's this hydrogen bonding and the lattice and that sort of diamond net-like shape that it creates that means that the molecules get further away and expand when it's cooled down. When in reality, the energy is getting lower, it should contract. So, water should only exhibit these dipole-dipole interactions between positively charged hydrogen and the negatively charged oxygen. It should have weak bonds. It should have a relatively low boiling point. I think around 36 degrees, 37 degrees. So room temperature basically. But it also has hydrogen bonding. And I will talk about proteins and DNA later on, just to make it a little bit more interesting, so it's not just talking about water. But it also has hydrogen bonding, which means that these positively charged hydrogens are attracted. Well, actually, I don't know which one's attracted to which. But you've got these lone non-bonding pairs of electrons on the oxygen, and these are make oxygen very, very reactive, and everything wants to bond. So that's the difference between polar covalent and dipole-dipole bonds, which are just positive and negative, just normally interacting with each other. And then once the electron's made its way back around, it just bond dissipates. When we're looking at the water here, we have a virtually permanent dipole. So the hydrogen will always be positively charged, and the oxygen will always have these two extra non-bonding pairs that make it extremely reactive. I wouldn't say reactive, but extremely attractive to these positively charged hydrogen. So when hydrogen is bonded to a very electronegative atom, this will produce a strong partial positive charge on the hydrogen. So we know, we go all the way back to the basics, when an atom loses its only electron, or an outer shell electron or a valence electron, it becomes positively charged. The oxygen is bound to 2 hydrogen, so it gains 2 electrons. So these are attracted to the partially positively charged hydrogen atom on another molecule, and these form a bond. So I'm gonna give you 30 seconds to have a think and how you would explain what a hydrogen bond is. What is required in order to have a hydrogen bond, that's supposed to say. Not what is required to hydrogen bond. And then I will go through what the hydrogen bonding looks like in water and what it looks like in ammonia, the 2 most common ones. So I'll give you 35 seconds. Just have a think. So what is a hydrogen bond? It's the interaction between partially positively charged hydrogen and the lone pairs of electrons on either oxygen, nitrogen, or fluorine. So what's required? Well, you need hydrogen, oxygen, nitrogen, and fluorine. So, or fluorine. So if we were to draw them, out, how they bond. So you have something like this. I'm sure you can all remember how good my drawing is. So you have the hydrogen, and then you would have let me stop sharing that. So we know that this is negative and positive, and you end up with these 4 tetrahedral molecules. And I'm trying to draw as best I can. And then you have so you get this tetrahedral molecule shape, and they join to other tetrahedral molecule shapes, and that's sort of what holds water together. And it's this crystal shape that they make. I mean, that's a terrible drawing, but you can see that if I could draw properly, it would take up a diamond shape, and then more of these just come across and slide in and bond. And the surface tension of water is, again, if we were looking purely at polar covalent, then the surface tension of water wouldn't happen. But we can see that there's all kinds of like certain bugs, spiders, they spread their weight out enough and they can walk across the water. And that is the due to the surface tension. If you drop water onto a coin on the desk, you'll see it'll make a dome until you add too much and it breaks. And it's only able to do that because of this hydrogen bond. I'll keep saying that word till my head explodes. So, water and water, NH3, so ammonia. And if we think about it, water is in group 6, so we combine with 2 hydrogen. Nitrogen is in group 5, so you combine with 3. So, same thing again. So hydrogen, positively charged, hydrogen, positively charged. Negatively charged, with lots of electrons ready to bind. So then we have another NH3 molecule. And you see 3 plus, 3 minus, very strong bond. And they would just keep lining up and lining up and lining up in that sort of fashion. So, they're the examples of the hydrogen bonding. So what do you, again, here is a 30-second timer. What do you think the trend is? Yeah. Think the boiling point would increase? That could be one of the tutorial questions. So as the number of electrons increases in anything bound with hydrogen, what happens to the boiling point? So the biggest impact of hydrogen bonds is the impact on boiling point. To use a more simple way of looking at it, so ethane has a boiling point of minus 89 degrees Celsius. Now, if we get rid of this H and we replace it with OH, we make ethanol. Ethanol. And what do we see here? We see oxygen bound to hydrogen. Now, the boiling point of ethanol is 76 degrees Celsius. All we've done is made it an OH on the end, or hydroxide group. So we know that ethanol has an OH group, or a hydroxide, or hydroxyl. So we know that it can exhibit hydrogen bonds. And the difference between, what's the word? Dispersion forces well, we have a boiling point of minus 89 with hydrogen bonds, we have a boiling point of 76 degrees Celsius. So you can see the marked impact that the hydrogen will have on the boiling point. So, and this touches on boiling point a little bit. But basically, the stronger the bonds between the molecules, the more energy required to break them. Therefore, the higher the boiling point. So H2O, HF, and NH3 all shouldn't have, I don't know why that's not. So they are all, shouldn't be, the boiling point shouldn't be that high. So if we look at the molecular weight of water, is 18. In group 6 with the other oxygen, so with oxygen, there is a compound there with a molecular weight of 130. Yet its boiling point is -2. So if we look at HF, molecular weight is 20. It doesn't quite match, does it? So NH3, molecular weight of 17. These all exhibit hydrogen bonds, and that is why they are the anomaly in that group. So you bond hydrogen with oxygen. It's just not the same with sulfur and selenium. I don't know what T is. And same with the rest. These do not follow the trend of molecular weight versus boiling point. And if you see that, you know there's something more at play than dipole forces. So this is what should happen. You increase the molecular weight and the boiling point increases. And that's because there's more electrons present for those interactions to occur between. So that's what it should look like. So this is in group 4. Large molecules have greater forces due to more electrons, so they have a greater dipole. So group 5, NH3 should not be there. So if we look at the molecular mass of NH3 here, and then we go to, oh, I can't remember what that one is, or what these are, but the molecular weight is 15, and it's got a higher boiling point of the next compound, which has a molecular weight of 70. So there must be an additional intermolecular force, and we know that this is hydrogen bonding. So again, H2O is even higher in group 7. It has virtually no molecular mass and a boiling point of 100 degrees. Whereas in group 7, you have a compound 130 and it's 0 degrees Celsius. So there must be an additional intermolecular force there. And again, we know because it's hydrogen bound oxygen, it's hydrogen bonding. So HF, again, hydrogen fluoride or hydrofluoric acid. It should really have a boiling point well into the minuses. It should be down here somewhere. If we're looking at this graph and following the trend in group 7. So all of them buck the trend for the rest. So oxygen, H2O, hydrogen fluoride, and NH3. They don't make sense unless there's an additional intermolecular force, and obviously we know that is hydrogen bonding. So why do oxygen, fluorine, and nitrogen form such polar bonds with hydrogen? That is in the second tutorial question for this one. So again, clue, what did I say causes this permanent dipole? So we talk about ice, water. Water shouldn't exist in the states that it does. When we take out, because then there's sort of diamond tetrahedral lattice upon lattice upon lattice, the water molecules can't move about freely, so they're locked in place. And the molecules, in order to fit into this structure, are less, they're packed in less closely than in liquid water. So ice is less dense than liquid water. Everything else shows the opposite trend. Becomes more dense when it becomes solid. So that's why we have massive, what's the words? The icebergs. There we go. So tetrahedral formation. And it has this weird, I don't know if you've ever seen ice under a microscope. It's actually really quite beautiful. That's why snowflakes can have their cool little patterns on them. And they actually increase in volume and they increase in density. Like I said, put a plastic water bottle in the freezer and you will end up with broken or very deformed water bottle. So, the melting point of ice is relatively high, as is its boiling point. And that's because of the strong hydrogen bonds between the H2O molecules, which is on top of the van der Waals forces and the dipole-dipole forces, and you've got the hydrogen bonding as well. So high surface tension is why some bugs can run across. It's why water has its buoyancy level that it does, and explains the low viscosity. So I'm going to explain the first one. This will be the third tutorial question, and the rest of these will follow this now that I've had a bit more time to put them together. So why do you think water is such a good solvent? It's because of the extremely polar bonds, so the very positive hydrogen and the very positive, very positive hydrogen, very negative oxygen. So anything that's polar and anything that exhibits hydrogen bonding can be dissolved by water. So I want you to elaborate on that for me. Why? How does it happen? And we'll go through solubility next week. It's just a good little lead into it. And draw a diagram to show how water dissolves sodium chloride. So, this is sort of jumping ahead, but it allows you to conceptualize what hydrogen bonding is and why it's important. So, the structure of a protein, the 3D structure, is the most vital thing to its function. Most genetic and inherited diseases are caused by proteins that don't fold properly because the genetic basis is incorrect. An example is something like sickle cell anemia, where the red blood cells don't form properly. And that's because the proteins that make up the red blood cells, namely hemoglobin, don't fold correctly because they are structurally incorrect. So proteins have lots of carbon double bound to oxygen, which is polar covalent, and nitrogen to hydrogen groups, which is hydrogen bonding. And so they can form hydrogen bonds, they can call disulfide bridges. And there's, I'll go into that. These hydrogen bonds hold the proteins into fixed shapes. So helix, beta sheets, and then further tertiary and quaternary structures. And protein, a denatured protein basically means a protein that's been unfolded. It's no longer functional. So usually that's done by heat or acid. And the more hydrogen bonds a protein has, the less likely it is to be denatured. So the stronger the bonds, hydrogen bonds, and other things, but we'll just stick with hydrogen bonds, the more temperature or the more severe the change in pH is required. So there's bacteria, thermophilic bacteria that can survive in thermal pools up to 96 degrees Celsius, I think it is. And thankfully there is, because we use that in all of our current PCR and molecular biology. things that if we hadn't found those, we wouldn't be able to do what we do now. But basically, once you heat a certain protein to a certain temperature, it's no longer functional. The hydrogen bonds break and it just falls apart. I'm going to go a little bit into biochem now, just to try and conceptualize this. So primary structure is just the chain of amino acids. So letters and numbers, it doesn't mean much. Secondary structure, you get these, and you get these bonds forming, hydrogen bonds that hold this all together. Hydrogen here, hydrogen here, hydrogen here, hydrogen bonding here. You have the tertiary structure, where you get ionic bonds between negatively and positively charged, and you also get more hydrogen bonding and disulfide bonding. And it eventually creates this is hemoglobin. And these are where the oxygen and CO2 attach to be transported. And basically these have to be folded really, really specifically, otherwise they don't work. So they need to have that hydrogen bonding in place in order to stay together. So for the formation of these structures, we have hydrogen bonds between oxygen and nitrogen and hydrogen. Ionic bonds, disulfide bonds, which are two sulfur bonds between two sulfur atoms, and van der Waals, or your dispersion forces. So when we're talking about in proteins, it forms between the negatively charged oxygen here, between oxygen and carbon, and then we have nitrogen and hydrogen here. So it's not that typical one that we talked about, it's a bit more complicated, but the principle is the same. You have a positively charged hydrogen and a negatively charged oxygen that has spare electrons that are non-bonding. So high temperatures and altered pH split this bond and you denature the protein. So disulfide is just a covalent bond between two sulfur atoms. I mean, I won't go too deep into that because we're doing biochem in a couple of weeks. Van der Waals forces, what we talked about. And it's a weak forces of attraction between non-polar molecules. So the R groups of the amino acids, or phenylalanine and valine. And again, they are weak. So if you increase the temperature, you'll break these bonds. Okay, so thank you everybody. That was hydrogen bonds, and probably one of the more important concepts that we'll go through. So I mean, you're watching this, it's already up. And I'll get some other videos up as well. So thank you for watching.